Hello, good morning. Okay, so let's wait for a little bit. We will start in like within 1 minute. So today we will talk about gambler's ruin and then random walks, and these topics are very similar to what we have studied before. How to use a Markov chain to help the analysis of some problem. Okay, so let's start now. So today again it is a lecture summary. So if you want to know more, so you can check out the the videos from the last year. So it should have better explanation. Okay. So first of all, we will describe what is meant by the gambler's ruin problem, and then we will, for this one, we will introduce what is meant by a stationary distribution, and then there are some sufficient condition for a Markov chain to achieve a stationary distribution. And then we will also talk about random walks as the second example. So here, let us consider this game. Let's say there are two players. One of them has L1 and then the other has L2. These two players are going to play a betting game. They have a fair coin. And then for this coin, let's say if head comes up, the first player will win $1. And then if tail comes up, this first player will lose $1. So when he wins $1, the other player will get $1 fewer. And on the other hand, if the first player loses $1, it means that the second player will gain $1. Okay. And in this game, suppose that it is going to play until one of these players will go bankrupt. So when one of the player will have $0 left, then in this case the game will end. So we want to find out what is the probability that player one will win this game. So as we can see, it really depends on the money that each player has. So if a player has more money, then in that case the probability should be higher. Okay, so this game is a perfect example of a Markov chain scenario. So we can model the game by using the following Markov chain. So here, each of the state is labeled by the money of the player one. So the player one could have $0, $1, $2. Okay, so this is not exactly the money that the player one has. It is the money that the player one has gained when the game starts. So he may gain $0, $1, $2, up to L2. In this case, the second player will have no money left and the game will end. And on the other hand, if he loses money, it could be like -1, -2, -3, up to minus L1. And if it is reaching minus L1, it means that the player one will have no money left and the game will also end. And because we are dealing with a fair coin, so at any state in the intermediate part, it will always have equal chance to go forward by one step or go backward by one step. On the other hand, if it reaches the endpoints here or the endpoints here, then we will not escape anymore. So with probability 1, we will stay in the same state forever. Okay, so we have this. This is the Markov chain. So, so yeah, you can check the conditions about the Markov chain. So it is independent of the history. We just need to know what is the current state, and then we can decide the probability of going to which other state. And it is also independent of the time. So no matter you reach this state today or you reach this state maybe 10 days after, whatever, as long as you are in the current state, you will have the same probability of going forward and same probability of going backward. Okay, so we will see that, okay, suppose that the game starts, yeah, when we have no flip. So in that case, we will be at state 0 when the game starts. Let's define some notation. So we let pjt, so this t represents the time, okay. Pj means that the probability that we are at state j, okay. So what is the chance that we are at state j after we have run t steps? So we will use this pjt to denote such a probability. And then let's say the q is the probability that we want to find, the probability that the game ends with player 1 winning. So when player 1 wins L2, the game will end, and then we say Q is the probability of this going on. So first of all, we have an interesting observation. We will see that when t goes to infinity, so when we are playing this game again and again and again, so when we play enough number of times, then there will be no chance of staying in the intermediate state. It is because whenever we are at this state, or whenever we are at this state, we cannot escape. So when the game is played for long enough time, we will be either in this state or in this state. We will not be staying in the intermediate part. We will be attracted to the state and then stay here forever, or we will be attracted to this state and stay here forever. So in that case, when t tends to infinity, when we are playing this game sufficiently long time, then apart from the intermediate state, apart from the extreme state, we will not have any probability. Okay. On the other hand, the chance that we're at the first state, this state, by definition, it is going to be 1 minus q, because it is the case that player 1 is losing, and the chance that we are here will be equal to q. So we have established these three relationships, and like the two sets or three sets example, we can establish more relationship between the states for the intermediate part, so that we are going to solve exactly what is the value of q by using algebra. Okay, so this time, let us use the expected value approach. So we let Wt to be the money that player 1 has after t steps. So initially, when we have t is equal to 0, the money that player 1 has won will be equal to 0, because the game has not started, so he's not winning any or losing any money, so the expected money at this stage is equal to 0. But then you will see that no matter what happens, the expected money that you are going to win whenever you are at any stage will be equal to 0, because there is half of a chance that you are going to fall forward one step, half of a chance you are going backward by one step. So in that case, half of a chance you are adding 1, half of a chance you are minusing 1. So in the end, it adds up to 0. And it is actually true even if you are at this stage L2, because for any chance that you have, you are staying here forever. So in that case, you are neither winning nor losing. So you are not going to move up or move down. So the expected winning that you will have for this particular step is equal to 0. On the other hand, okay, so we will see that there is another way to compute the expected value of the winning. So it is actually by using what? By using the definition of expected value. So let's say there is some chance that you are at this stage, some chance you are at this stage, and so on and so forth. The expected winning that you have after t steps will be the corresponding probability of landing at this state multiplied by minus L1, plus the probability of landing at this state multiplied by this value minus L1 plus 1, and so on and so forth, plus the probability that you are landing at this state multiplied with the value of L2. So this is by definition the what? This is by definition how we can define the expected value. And on the other hand, this is by definition of what? By definition of linearity of expectation. So because each step you are winning $0 expected, so accordingly, after t steps, the total winning will be expected to be equal to 0 as well. So now we have this equation and this equation so that we can combine them and find out that 0 is equal to expected value of WT. And then we take limit of t equals tends to infinity on both sides. So this is remaining to be 0. This is now becoming, we can now plug in the value of probability of j at t steps. It will be equal to what? Normally it is equal to 0 for all the intermediate case, and then it is 1 minus 1 for the first state, and then q for the last state. So we will have this equation. 0 is equal to this one. So after rearranging the terms, then we will see that Q is exactly L1 divided by the sum of L1 plus L2. So it looks like it is really a fair game because the more money you have, the more chance that you are likely to win, and then it is proportional to the money that you have. So for instance, I have $3, you have $5, the chance that I'm winning is exactly 3 over 8. And then if I have $10, you have $100, the chance that I'm winning will be 10 over 110. So it is proportional, really proportional to the money that the players have. Okay, but then this is actually for the case of a fair coin. It is going to be more interesting if we are going to analyze the case that the coin is not fair. We will have an exercise for you in the coming exercise, and then you will see that if we have a different coin, it is not fair, then suddenly it is not like a ratio between the original money that you have. It is going to be the one that has more money will have exponential advantage to the other player. So here you don't have exponential advantage. It is like linear advantage. But then you will check out how we can win more if you have more by using a biased coin. Okay, so this is the gambler's ruin problem. So let me check if you are okay with this. Okay, so far so good, right? Okay, so if you don't have any problem, let's continue with the stationary distribution and also the random walk. Okay, thanks. Okay, let me get back. Okay, now let us consider this particular small example of a Markov chain. So you just have 3 states, and then so this is the probability. So if you are at state 2, you must go to 0 at the next state. And similarly, if you are at state 1, you must go to state 2 in the next state. And if you are at state 0, half of a chance to go to 1, half of a chance to go to 2. Now suppose that at a certain time, we find that there is 0.4 chance you are at this state, 0.2 chance that you are at this state, and 0.4 chance that you are at this state. 0.4, 0.2, 0.4. So what will happen for the next state? I mean, what will happen after one more step? So after one more step, because this is 0.4, remember 0.4, 2, 4, okay. So you will have 0.2 chance going to 1. And this is the only probability that you can go to 1 in one more step. So you will see that at the next time, you will have exactly 0.2 chance of staying at 1. And then similarly, how about the probability of going to 2 at the next state, at the next step? So originally 0.4. 0.4, there is half of a chance going to this state here. So 0.4 times 0.5 is equal to 0.2. And here, there is another way to go to this state by taking the probability here 0.2 and then multiply by 1. So you get another 0.2. So in the end, you will find that after one more step, you will have 0.4 chance to be at state 2. So after one more step, you have 0.2 chance here, 0.4 chance here. So that means that there are going to be 0.4 chance here. So interestingly, that means that if we are now at a certain scenario that we have 0.4 chance, 0.2 chance, 0.4 chance here, then this distribution of probabilities will remain the same after one more step. And in such a case, we call this distribution a stationary distribution because it will stay here forever. Yeah, this is what I mean. So if PT represents the distribution of the current time t, then pt plus 1, this is the distribution at the next time, t plus 1, it remains the same as pt. And in such a case, this is called a stationary distribution. So not all Markov chain has stationary distribution. Some will have, some will not. And then some will have more than one stationary distribution. Some of them will have exactly one, and then some of them will have zero, non-stationary distribution. But then one criteria to decide whether a distribution is stationary is just this checking. We want to check whether pt plus 1 is really equal to pt. And then we have a formula for computing pt plus 1 based on pt, which is by using this one. So this is how we can obtain pt plus 1 based on pt. So if pt times p is equal to pt, then that means that it is a stationary distribution. So how many of them? Yeah, some of them has, some of them doesn't. And it can be more than one. It can be exactly one. So for instance, let's take a look of this case. This is the Markov chain that we have just seen. We will see that if the distribution originally starts with 1, 0, 0, 0, then in that case, this is a stationary. And similarly, if we have 0, 0, 0, 1, then it is also another stationary distribution. Indeed, as long as all the intermediate states here, they are all 0, and then let's say we have a probability p here and the probability 1 minus p here, then this is also a stationary distribution. So this is an example to see that some Markov chain may have more than one stationary distribution. And then this is another example. So this Markov chain has infinite number of states, so it is not a finite Markov chain. And then we will see that if you are at state 0, the next time you must go to 1, and similarly, if you are at state 1, the next time you must go to 2, and so on and so forth. So you can see that there can't be any stationary distribution, because if you have a certain probability distribution here, it must not be the same after one more step. Okay, the leftmost non-zero entry which will be changed to a 0 after one more step. So it can't be having any stationary distribution. Okay, now what we want to do today here is that we want to introduce some conditions that will tell if a Markov chain has a unique stationary distribution. So as long as some conditions are met, it will have a unique stationary distribution, exactly one. But then it doesn't mean that it must be meeting this condition to have a unique stationary. Okay, so we are going to give a sufficient condition that allows us to check if a Markov chain has a unique stationary distribution. So we have two concepts that we want to describe. So one of them is called irreducible. So a Markov chain is irreducible. This is a very easy idea. Irreducible, it means that if you start from any state, then you can go to any other state. So in graph theoretical terms, it means that the graph representing the Markov chain is a strongly connected graph. Okay, so each vertex can go to any other vertex by traveling along the directed edges. So for instance, 0 can go to 1, 0 can go to 2, 0 can also go back to 0. So it requires that every state can go to any other state, including itself. Now actually, this example is easy to see. It is because you can see that there is actually a cycle connecting all these three vertices. So each vertex can go to any other place. But if we look at this example, this is not an irreducible example because from state 2, you can only go to state 2. You can't go to 0, you can't go to 1. So this is not an irreducible case. Okay, so this is the definition of an irreducible Markov chain. Okay, now the second one is called periodic. So a Markov chain is called periodic if you can find some state. You don't need every state, you just need some state such that for this state, it is interesting. Whenever this state can travel back to itself, it must be of some multiple of some number d, where d is greater than 1. So we will see an example soon. If this is the case, then the Markov chain is periodic. And in the opposite case, where none of the states, so every different state, okay, you don't see this behavior, then the Markov chain is called not periodic or aperiodic. So let's see an example. So let's check out the right hand side. Okay. Now for state 0, it goes back to itself after each step. It can only go back in one step or in two step or three step and so on and so forth. But then this doesn't say that it is aperiodic or periodic. It is because periodic, it requires that it must come back to itself in some multiple of d greater than 1. Now, but on the other hand, so this is not periodic. So state 0 is not periodic. But how about state 1? For state 1, so you start here, so it can come back in 2 steps, or it can come back in 4 steps, or it can come back in 6 steps, and so on and so forth. So in such a case, we will see that for state 1, every time it comes back, it must be a multiple of 2. So in such a case, state 1 here is periodic. And similarly, for state 2, it can come back in 2 steps, 4 steps, 6 steps, and so on and so forth. So in this case, state 2 here, this state 2 here, excuse me, there's a lot of messages. State 2 here is also periodic. Okay, now how about this one? So we were claiming that this is not periodic at all. So we will need to check for every state here, they are not periodic. So for state 0, of course, it can come back in 3 steps, but then it can also come back in 2 steps. So we can find that when it can come back in 2 steps, it can also come back in 3 steps, then it doesn't mean that every time it comes back, it must be a multiple of some d. Because 2 and 3, they are not having greatest common divisor to be greater than 1. So in that case, state 0 is safe. So it can come back in 2 steps or 3 steps. Okay, so okay. Now how about state 1? State 1 is it can come back in 3 steps, and then we can see that it can also come back in 5 steps. So 1, 2, 3, 4, 5. Now the greatest common divisor between 3 and 5 is 1 only. So again, state 1 is not periodic. So it is not like it comes back in 3 and 6 and then 9 and then 12 only. It can also come back in 5 steps. So in that case, 3 and 5, it doesn't have any greatest common divisor. So in such a case, state 1 is also okay. Now state 2 is similar to state 0. It can come back in 2 steps. It can also come back in 3 steps. So state 2 is also not periodic. Now when every state here is not periodic, the whole Markov chain, we call it aperiodic. Okay, so there is a theorem. I'm not going to prove it because I don't know how to prove that, but this is some known result. Suppose that we see a Markov chain which is finite, and then also it is irreducible and aperiodic. Then finite, irreducible, aperiodic together will imply that this Markov chain will have a unique stationary distribution. It must have a stationary distribution, and the stationary distribution is unique. There's only one. Okay, now suppose that we use pi 0 to represent the stationary probability at state 0, pi 1, the stationary probability at state 1, and so on and so forth. Then we will also have another interpretation of this value of pi. So pi k, the probability, is also equal to the so-called the inverse hitting time, 1 over hkk. So here, hkk represents what? It represents that this is the expected number of steps that we start from state k and coming back to state k again. So this is called starting from k, ending at k, expected time that we need to do so. And then pi k is equal to, it turns out that it is equal to the inverse of hkk. Okay, so this is the result that we will be using when we talk about random walks. But basically, this is the important part. As long as it is finite, irreducible, and also aperiodic, then the Markov chain must have a stationary distribution, and it is unique. So let me double check if you are all okay so far. Okay, so I don't see any questions, so let me continue. So we are now moving to the final topic for today's class. Okay, now random walk. So for random walk, it is random walk on a graph. So we have a graph G, and then this graph G, we assume that it is finite, undirected, and connected at the beginning. What we are going to do here is we are going to imagine that we are at a certain location, at a certain vertex on this graph, and then we are going to walk along the edges randomly. So we want to first do some transformation of this graph to make it a directed graph, because we want to make it look like a Markov chain, so with directed edges. So what we are going to do here is we are going to replace each undirected edge by a pair of directed edges. So here it's like this. So if this is the graph G, we are replacing this undirected edge by this one and this one. So a pair of directed edges that tell us that we can go from 0 to 1 and also from 1 to 0. So originally it's just an edge, but here it is, we can go from 0 to 1 and 1 to 0. And then also, so by this case, we are actually transforming this into some Markov chain. Once we can assign the probabilities of traversing each edge. So how do we assign the probabilities? So here is simple. For any state here, it has going to be equal chance to go to use each of the directed edge that is joined that is starting from this node. So for instance, for this 0, there are two neighbors here. So we will see that for 0, there are going to be two directed edge. Okay, so for this 0, we are going to have equal chance to visit the next state by using these two arrows. Is that okay? So it's 1 over 2 and 1 over 2. And then for this state 3, original graph, it has 3 neighbors. So in that case, what does that mean? It means that it will have 1/3 chance, 1/3 chance, and also 1/3 chance to visit each of the next state. So this is a so-called random walk on a graph. So an easy interpretation is like this. So we are actually using this graph for the traveling, and whenever we are at any state here, let's say 3, we are going to throw a die. With equal probability, we will pick this edge, and this edge to visit next. Okay. So here, because the original graph G is assumed to be connected, so that means that the corresponding Markov chain here must be irreducible. It must be strongly connected. Right? Easy. Yeah, because there is a way to travel from any node here to any node here by following the undirected edge. So in the corresponding graph, there must be a way to travel from any node to any other node using the directed edges. And also, as long as there is one edge, okay, we don't consider a graph with nothing. Okay, so that means that each vertex must be connected by some one edge. So each vertex can also go back to itself by going through the edge and going back itself. So each vertex can go to any other state, including itself. So it means that the graph is irreducible. And then if the graph, the random walk graph itself is also aperiodic, we will be seeing something interesting. So here we have a lemma. This lemma says that this right-hand side graph is aperiodic as long as the original graph is not bipartite. So recall what is a bipartite graph. So a bipartite graph is a graph such that there is a way to separate the vertices into two groups, or to color the vertices into black or white, such that all the edges are joining different colored vertices. Okay, so this is the way that we define what is meant by a bipartite graph, but there is an alternative definition. So if a graph is not bipartite, it happens if and only if there is no odd length cycle. Okay? Did I make a mistake? So once again, okay, a graph is bipartite as long as it doesn't have any odd length cycle. On the other hand, a graph is not bipartite. It means that there must be some odd length cycle. Okay, so we can see that this is actually an alternative definition of a bipartite graph. This is based on the property. So using this, we will see that if the original graph has an odd length cycle, then what does that mean? So each vertex, let's say this is the case, there is an odd length cycle in the original graph. Then it automatically implies that the graph here, the Markov chain here is aperiodic. It is because, first of all, each vertex can go back to itself in two steps. So there is a way that it go back to itself in two steps. And the second case is that there is a way for any vertex to go back to itself in odd number of steps. Now, because if there is an odd length cycle, like this one, then any vertex, let's say this one, there is a way to go to some vertex that is on the odd length cycle, travel the odd length cycle, and coming back to itself using the same way that it goes to the first node here. So 2 can go to 3. This is the node that is on the odd length cycle, travel the odd length cycle once, and go back in the original way. So we will see that this part is even because we go and back, but then we travel the odd length cycle once, so this part is odd. So an even number plus an odd number is an odd number. So that means what? For any vertex that we see in this graph, there is a way for it to go back to itself using odd number of steps. And then we can see that it can also go back to itself always using even number of steps. So odd and even doesn't have a greatest common divisor greater than 1. So in that case, every vertex is not periodic. So the graph is aperiodic. So this is the proof. Yeah. So you can check it. Now, if this is the case, then we will see that we assume that, okay, so we assume that the original graph is not bipartite to make sure that the corresponding random walk is aperiodic. And then because this is connected, so we have irreducible. So it implies that the random walk on G will have a unique stationary distribution. And moreover, what we know here is that this unique stationary distribution, the pi v, can be computed super easily. This pi v actually is proportional to the degree of the vertex in the original graph. So if we are looking at this example, this has degree 2, this has degree 2, this has degree 3, and this has degree 1. So for this graph, the random walk of this graph will have a stationary probability, and the probability will be in proportional to the degree. So the probability here and the probability here will be the same because they are both having degree 2. And then the probability here will be 1 portion. The probability here will be 3 portion. So actually, in this particular example, the stationary distribution will be 1 over 8 here, 3 over 8 here, 2 over 8 here, and 2 over 8 here. So it is in proportion to the degree. And then because they sum up to 1, so it is going to be degree divided by the total degree. Okay, so how can we prove this? So we can actually prove this by brute force checking. Okay, so we are verifying whether this is going to be correct. Okay, so first of all, we examine whether this is a valid probability distribution, whether they add up to exactly equal to 1 for different v's. So it's good because 2e is the total degree. So each vertex gets a portion of the corresponding degree. So if we sum up all the pi v's, it is going to be the total degree divided by the total degree. So it is equal to 1. So this is a valid probability distribution. And the next part is we just need to double check whether this is a stationary distribution. So we want to check what happens if we multiply this distribution pi by the transition probability matrix P. Okay, so we want to find out what is this pi times this big P. So here, so P is the transition matrix, and then we let n of V to be the number of neighbors. So okay, so not the number of neighbors. So this is the neighbor set of V, not including itself. Okay, so that means that the size of NV, which is equal to the number of neighbors, is exactly degree of V. And now let us examine what is the the entry of this one. So the weave entry of this one will be the probability that we are going to be finding us at state V in the next step. Okay. So we first assume that we are already in this probability distribution pi, and we will see what happens for the weave entry in the next step. So in order to compute the weave entry, we need to find out for different states, what is the contribution? What is the chance that we will contribute to the probability in the next step? So here it is like we need to sum for the chance that we are at state U now, multiplied with the probability that we will move from state U to state V. Okay, so this pi U, Pu, V. Okay, and then we will see that, okay, if some node is originally not a neighbor of V, then in that case, there is no chance for this vertex U to contribute to anything in the next probability for V. So in that case, although we need to sum for every U in the graph, we just need to focus on every U in the neighbor set of V. So these two are the same, yeah, because for the other case, it is going to be 0. So after simplification, we will find this is the case. So what is pi U? Pi U by our choice, this is degree of U divided by 2 times the edge, so the total degree. And what is PUV? PUV is the chance that you are moving from state U to state V in the next step. And then, because this is a random walk graph, we will see that for state U, there is equal chance to go to each of the neighbor of the U. So in that case, the chance that you particularly choose V as the next step, it is exactly equal to 1 over degree of U. And then we will see that degree U here and degree U here cancels each other. So we will find that it is 1 divided by total degree in each of the terms here. And how many terms are there? There are the number of neighbors of V terms here. So each of them contribute 1 over 2e. So in that case, it is degree of V divided by 2e. And then this is pi V. And then this formula does not specify which V we are talking about and which U we are talking about. So in that case, we will see that for any vertex V, pi V will remain to be the same after one more step. And so pi is equal to pi p, and it is a stationary distribution. And why is it unique? Simply, it is because the random walk graph here is aperiodic and irreducible. Okay, so done. So far, let me see. Let me see if you're okay. So I'm talking a little bit fast. So far, no question. Yeah, so let me continue. So we will end the class after the description of a few more slides, and then we are good. So we can have lunch earlier. Okay, now, and if you are really tired, yeah, if you want to take a break, yeah, go ahead. Yeah, because this is recorded, so you can come back and view the remaining anytime that you want. Okay, now we now know the pi of v is exactly the degree of v divided by total degree. So we can now also find out that HVV by our previous theorem, the expected number of steps that we start from v and then coming back to itself is the inverse of pi v. So it is going to be total degree divided by degree of v. And now we want to do something more. So the previous theorem tells us only HVV. So the expected step to go from v back to itself. We are actually interested in doing some random walk so that we can travel to all the vertices of the graph, starting at some vertex. So in such a case, and then we want to find out what is the expected number of steps of doing so. So in general, we want to find out what is HVU. What is the expected number of steps that we start from V and then go to U. And then, yeah, so let's have a lemma for this one. We claim that if there is an edge, that is directed edge between U and V, then h of uv cannot be a lot. It is less than 2 times e. So we are going to make use of this result to have more, deduction later. So this huv is less than 2 times e for any uv. So let's go through the proof together. We let nv to be the neighbor set of v, and then we will see that hvv itself can be expressed by what? So in order to find out the expected number of steps that we can start from v and go back to v itself, then we will see that there is equal chance that we will visit any of the neighbor in the next step. And if we visit a certain neighbor u, let's say, in the next step, then we will see that the chance that or the expected number of steps that we go from that stage u back to v. So this is to complete the case of HVV, right? Is HUV steps. So we use one step to move to the next state, and we use extra H of UV steps to go back to V itself. So this is actually the expectation, the definition of the expected value. So there is the same chance to go to any vertex u in the next step, as long as u is a neighbor. And then if we go to u, then the total number of expected steps, so this is actually linearity of expectation, is equal to 1 plus h of uv. And now, what is this value? This value itself is equal to 2 times e divided by degree of v. This is equal to 2 times e divided by degree of v. HVV itself is 2 times e divided by degree of v. So if you go back, this is equal to 2e divided by degree of v, so that the summation here is actually the same as 2e. And among this summation, one of the term is HUV, and then they add up to exactly 2e. So in that case, any term here must be less than 2e. So we have a very crude bound. So it is not accurate bound for this case, but then, yeah, it is sufficient for us to do the further analysis in the next slides. Okay, so we have two things. Okay, go back to itself, we have an exact bound of the expected value. Going to the neighbor, we have a crude bound. So we are going to make use of these two together to do some analysis. So the last concept here is called the cover time. This is what excuse me, sorry. Let me go back. Yeah, where is it? So go back to this one. Okay. So it's cover time. So cover time means that I want to travel to every places of this graph at least once. Okay. So we can define what is meant by cover of V. Cover of V specifies that V is the starting vertex. So if we start at vertex V, how long does it take to go through every vertex at least once? And then the cover time of a graph is the maximum amount all the cover times of the V that we can imagine. So the worst case cover time. Okay, so we are going to check if we are starting at the worst vertex. So maybe we are very unlucky. So what is the time that we need to walk through every vertex, including itself? So it must come back to itself. Okay. And so we are of course it can be it can be fast, it can be slow, but then we want to find out what is the expected value of this cover time. Okay. So we first consider so in order to get a bound, so we want to bound it, although cover time can be very bad, but then we want to give an upper bound that the cover time cannot be that bad. Okay. So here, let us consider any spanning tree T of the original graph tree. Okay, you can have any spanning tree T. And then we let rho to be an Euler tool that traverses each edge of the of this of this of this spanning tree T once in each direction. So let's see, do I have a graph here? Okay, so perhaps I don't have a graph. So perhaps let's use the example that we have. So for instance, let's take a look of this one. This is a graph G, and then we want to find a spanning tree for this one first. So any one. Okay, so let's consider this one. Let's consider a spanning tree with just this edge, and this edge. Is that okay? So we don't need this one. This is an extra edge. So there can be a lot of spanning trees, but let's say we are looking at a particular one. And then what is meant by an Eulerian tour? So we start from one vertex, we travel each edge exactly twice. So it's like this. For this particular example, we go here, come back, and go here, and then come back, and then go here, and then come back. So we will see that this is an Euler tour. Euler tour requires us to travel each edge exactly once. So imagine that we have a spanning tree. What we do here is that we replace each of the undirected edge by two edges in opposite directions. And then we want to find an Euler tour that travels all the edges exactly once. So it is one way of doing so. So you can also have another way, maybe like this. You go here, and then you go here, and then you go here, and then you come back. So this could also be another case. But let's roll here. So we start, okay, so let's do this again. So we have a spanning tree T. Based on T, we make an Euler tour on this tree T. We let rho to be the Euler tour. Okay, so using the Euler tour is a good way of traveling each edge at least once and coming back to itself. So let's say we use V0, V1, V2 up to V. So there are how many edges? There are exactly V minus 1 edges. So the total tour consists of 2V minus 2 steps. So V0 goes to V1, V1 goes to V2, and so on and so forth. We come back to itself after 2V minus 2 steps. Okay, we let this to be the sequence. Now, based on the tour, we can see that one way of completing a cover starting from this V0 is you try to go to V0 to V1, whether it has been visited or not before. Let's say we must consider V0 first, go to V1, and then V1 goes to V2, V2 goes to V3, and so on and so forth to finish this covering. So for instance, let's go back again to our example graph. The t here is this one, this one, this one, and suppose that the tool here is 3 to 0, 0 to 3, 3 to 1, 1 to 3, 3 to 2, and then 2 to 3. So we are going to cover this graph in the following way. We must first go from 3 until we meet 0. So we may be unlucky. We may go to 3 and then 1 and then 1 to 3 and then 3 to 2 and then 2 to 3 and then 3 to 0. It could be something like this. And in such a case, we will count that it takes 5 steps from 3 to visit to 0. Is that okay? So our covering is not the clever covering. We are going to cover in the following order. First, we start from 3 and we must next go to 0. If we go to any other node until hitting a 0, then we don't count as successfully traveling to those vertices. And then after that, we must go from 0 back to 3. So maybe 0 can go to 1, 1 can go to 3, that's good. Then we will count it as 2 steps. But maybe 0 go to 1, 1 go to 0, 0 go to 1, 1 go to 0, and then 0 go to 3, then we will count it as 5 steps. Is that okay? And then after that, we must go from 3 to 1, and then after that 1 to 3, and then after that 3 to 2, and then 2 to 3 to finish a particular walk. So obviously, this walk is one of the ways to cover the graph, but this is not the cleverest way to cover the graph. So in that case, the expected time for this so-called tour that we are restricted, we must go from, we must agree with how the spanning tree T and the row, the Eulerian tool of T defines. It must have at least cover time of V0. Yeah, because for V0, cover time of V0 is the cleverest way. We will not need to follow any restriction as long as all the nodes are hit, and then we can come back to itself. Then this V0. As long as all the nodes are hit, then it is already okay. But then in the restricted case, then we need to travel more. So the what we are traveling must be at least cover of V0. And so we will see that this is the expected number of steps that we need to travel in the restricted way. And then this is less than what? This is less than there are 2v minus 2 edges, and then each edge, the expected time is 2 times e. So in the end, we will have a bound of 4 times v times e. Note, recall that this is the upper bound on the cover time starting at v0, and in fact it is independent of the vertex that we chose at the beginning. So we will see that the expected cover time of a graph must always be less than 4ve. So here we have the expected cover time of G is less than or equal to 4 times v times e. Okay, and so with this we can define a so-called algorithm for doing random walk on this graph G, so that we want to make sure that, not make sure, we hope that we can travel to each edge, travel to each vertices exactly, sorry, let me repeat. So we want to design an algorithm of doing random walk on the graph so that we expect we will hit every vertex at least once. So what we can do here is that we will see that the expected cover time is 4 times v times e. So in such a case, if we travel long enough, let's say this is 4 times v cubed. So 4 times v cubed is at least 8 times v times e, right? Yeah, because e is at most v squared over 2. So in that case, this is like the double of the expected value that we have. If we do a random walk of G starting from any vertex, let's say S, with enough number of steps, then we will have probability at least many. Okay, so here in this case, we have 2 times the expected value. Then in that case, by using Markov inequality, we will see that we will be traveling to each vertex at least once with probability 1/2. Okay, if this is more, let's say this is like like 16, then then we can argue that it is at least 8, 1 over 8 here. But we can be a little bit clever. Okay, so the clever part here is, if we are going to, like 4, we will have 1 over 2. If we change this to 8, we can think of this as 2 batches of 4v cubed. So in that case, the chance that we are not succeeding will be less than 1 over 4. So the succeeding probability will be 3 over 4. So if this 4 turns to what? Let's say turns to 100. 100. So 100 times v cubed, you can think of this as you have 25 batches of 4v cubed. So in that case, the chance that we are not succeeding will be at most 1 over 2 to the power 25. So that the chance that we are succeeding will be at least 1 minus 1 over 2 to the 25. Okay, so here, this is the case that we can use the analysis result here, the Markov chain bound that we achieved to analyze the behavior of a random walk of G. Okay, and actually this problem is called the ST connectivity problem in general. So in the ST connectivity problem, we're not covering the graph, but instead we start from some vertex S, and then we want to find out how we can travel to T. So if S and T can be connected by some directed path. So we will run this algorithm for a certain number of steps, and if the S and T are originally connected, then there is high chance that we will find T along the way. And if they are not connected, then of course we cannot find T in any case. So by doing this, we can turn this random walk algorithm into an algorithm that checks whether S and T are connected. Now this has some of great importance in the complexity theory. Okay, because the algorithm that we have just described is very space efficient. We don't need to memorize, because it is actually a Markov chain running. As long as we can have the input graph G, we can assume that this input graph G is read only, like it is, you cannot use the space of the input graph to do any other thing. Then the extra memory that we need to have is, we need to store what is the current state, so that we can update the next state again and again after each step, so that the space that we require to run the previous algorithm is a read-only input graph together with 1 or 2 counter that specifies what is the current state. So it takes only log of v bits to run this algorithm. So this is, in terms of space complexity, this algorithm is super great. It takes all the log v bits only. Okay, and now, why is it important? Yeah, it is because this is perhaps, yeah. So here, it is, we can see that this algorithm for random walk on an undirected graph, it takes only log v bits. But on the other hand, if we are having the directed graph at the beginning, so that some of the directed edges could be missing, then if we can solve, so a problem of the directed ST connectivity, it turns out that it is going to be the hardest problem that we can solve using only order of log v bits. And then it is the hardest in the case that we can assume that we are working with a non-deterministic Turing machine. So if you are interested in this one, yeah, search for dynamic ST connectivity, and then this is so-called, yeah, one of the hardest problem. Like we have clicks or vertex cover, they are the hardest problem that we can solve using a non-deterministic Turing machine in polynomial time. So here, this directed ST connectivity is the hardest problem that we can solve by using a non-deterministic Turing machine with using only this space complexity. Okay, yeah, I think, yeah, that's all. That's all for today. Yeah, so we are ending now. Let me see. Okay. Oh, why is it unique? So good question. So so I don't know. Yeah, this is a theorem. So as long as the corresponding Markov chain is finite, irreducible, and also aperiodic, then the stationary will be unique. So this is a theorem that somebody has proven. So I don't know how to prove it, but let's take it for granted. So recall that the graph that we are looking at here, we have an assumption. It is originally it is not bipartite. So in that case, aperiodic and irreducible are guaranteed. Okay. Okay. So yeah, if we don't have any further questions, yeah, let's end the class now. And then on Thursday we will also finish with another example of we'll finish the discussion of Markov chains by giving another example called Parando's paradox. And then if we have time, we can talk about the solution of exam 2. And then for next week, we are going to start with the probabilistic method. So we will be giving out also the homework for this Markov chains this week. Okay, thanks a lot. Yeah, thanks for coming. Okay, okay, see you again on Thursday. Bye.